Hey, so welcome back, and we're going to do some more LeetCode problems today. So essentially we're going to carry on and do more of these Blind75 problems, which is essentially just a really popular list of LeetCode problems. And within that problem list, we're going to be doing the graph algorithms associated with it. And so essentially the Blind75 list is just organized by different problem patterns and algorithms that you typically have to work with. And so we're going to focus on the graph algorithms on this list. Okay, and so essentially there's 6 questions here, and we're going to do all 6 of them. So the first one, we're given a 2-dimensional matrix and we want to count the number of islands. And so in this case, basically what you have here is 1 is representing a land block and a 0 is representing water. Okay, and so an island is formed basically by several 1s connected with like 0s that surround it, like so. Okay, and so you're essentially just counting all of the islands. So this would be basically 1 island here. Then if you have another 1 block over here, this then would be a 2nd island. Okay, and so to do this, what we're going to do is we're going to write a depth first search function just to explore every island, because whenever we find an island, we want to say, okay, we want to explore every piece of this and mark it as, okay, we've seen this before, so that when we find a new land block, we want to know whether we already have seen this land block and therefore this island before. Okay, so we're basically writing a depth first search function with a visited set just to keep track of what we visited before. And then all that we need other than that is just like, okay, we want to have an island count. So what is the current count, or what's the current number of islands we've seen so far? And so with each iteration, when we find a new island, we'll just increment it by 1. All right, so let's go ahead and implement this. So typically what you want to do is you want to get the dimensions of your grid like so. So let's just get the number of rows and the number of columns in our grid. And so we'll want to return at the end of this some like number of islands that we've discovered, so island count. And so initially we'll set this to 0 because we haven't seen any so far. And so we're going to want to search our 2-dimensional grid basically in every single direction, or I guess really like every single grid location we want to be able to visit here. So we'll iterate through this matrix, and with each iteration we want to say, okay, have we visited this land block before? And if not, we just found a new island. And so, okay, if this particular grid location is not in our visited set, and this is a island block, then that means we just discovered an island that we haven't seen before. So in that case, we'll call our depth first search function at this location. We also want to increment the number of islands that we've seen so far. All right, so let's go ahead and write out our depth first search implementation here, like so. So typically what you do is you define a function here specifying the grid location that you're currently on, and you just want to make sure that you're within the bounds of this matrix, like so. And so we're just saying, okay, make sure that the column range and the row range are within the actual 0 to the number of columns in this matrix. Okay, and so once again, because we don't want to be kind of infinitely searching our matrix here, we just want to make sure that we're still checking, okay, have we visited this place before, and have we made sure that we're only exploring land blocks and not exploring the surrounding water. Okay, and so if we get past this case, then that means, okay, let's go ahead and mark this as visited. So we just visited this grid location now, and then all that's left is we just want to explore the island in all 4 directions. And so we just paste this 4 times here. We want to explore upwards, downwards, to the right, and to the left. Okay, let's go ahead and run this, and oh, I just forgot a colon here. And not in visited, so we just want to define our visited set, right? So it's just a hash set. Oh, and index out a range. So for R, within the range of the rows, and 0 is within the range of the columns, So the only thing that matters here is we just want to make sure that we're specifying the column range correctly, like so. All right, so that's the first one. So essentially this runs in basically the number of rows times the number of columns in both time and space complexity, time and space. And that's because, well, you're going to have to search every single grid location in the space complexity because, well, in the worst case, your depth first search application stack will contain every single grid location kind of in that recursive stack, as well as this visited set could also contain the number of columns times the number of rows. All right, so that's the first question here. We'll go ahead and implement the second one. So for this, we're essentially given a graph and we want to clone it. And so this will be a deep clone of the graph. So you're not just creating a new graph that points to these existing nodes. You actually want to create a new node for every single node on this graph. And then you're essentially saying, okay, I want to use the same values that are on these nodes, but then also I want to make the same connections, but between these new nodes that I made. Okay, and this is what we would call a deep clone, not a kind of like light clone where you're just pointing to an existing graph. All right, and so to do this, what we have to do is we're just going to define a hash map, and it's a really clever trick. So we're going to say, okay, let's define a hash map here called old to new, and we're essentially using a pointer to point to the old graph and say, okay, what is the new node equivalent that on our new graph that we made for this? And it's essentially a mapping so that we can quickly look up in our lookup table and just say, okay, if we look up, okay, what's the new node for this old node? Oh, it's this one. And so as we construct our graph, we'll essentially have just a quick lookup table to see and look between our old and our new graph. Okay, so they're just mirrored edges of each other. Okay, and so essentially what we're going to do is we're going to iterate through our graph using depth first search, and then we're going to build our graph, our new graph, as we go along. And then finally, the last step is we're just going to basically build the edges between these nodes. And so the neighbors are really the edges between each node, and so we're going to have to define these edges. So initially we just build the nodes, and then we build out their edges and the relationship between these nodes. Okay, and so let's go ahead and implement this. So we'll go ahead and we'll do a iterative implementation of this solution. So we're going to have to say, okay, let's do depth first search iteratively. So we explicitly define our stack. So while we have something on our stack, we're going to want to pop the next node off our stack. And then from here, okay, we have our new node, and so we're going to want to iterate through all the neighbors. So for every neighbor in this node's neighbors, like so. So we're going to want to add each of these neighbors to our stack. But because this is depth first search and we don't want to end up in cycles here, just like we did last time, is we're going to find a visited set and just ensure that we haven't actually visited this particular node before. So we just say, okay, if this node is in our visited, let's just skip it. All right, now I'll just move me over here and move this like so. And so from this point on, so we're exploring using depth first search, but then how do we actually build our graph? So this is how we iterate through depth first search, but now we want to iterate through our graph here, or sorry, build our new graph. And so what we can say is, okay, well, we'll want to create that mapping here from old to new, because when we make a new node, we want to point the old node to it. And so we can define our hash map or a lookup table like so. We can just say, okay, then our old to new for this current old node is going to be mapped to our new node, which we'll define using this constructor here. And we're just going to pass in the constructor this old node's value. And so this basically makes a deep clone of this old node using its node's net value. right? And so that basically does this step of, okay, we just want to build our new graph as we go along here. Oh, like so. Great, and so the last thing that we want to do is actually build out the edges on our graph. And so to do this, we're just going to iterate through our lookup table here. So for every old and new node in our old to new hash map. And so we just call the dot items so we can get both the key and the value in our hash map here. And so to construct this, we're going to want to basically reference the old nodes and its relationships and all of its edges between each of those nodes, that we can basically make a deep clone of those edges just like we did before. Okay, and so we just want to iterate. So for every neighbor in the old node's neighbors, we're going to say, okay, then how can we clone these edges? And so we just want to basically say, okay, then the new neighbor's edges, so we want to add to its neighbors, it's going to be basically the lookup. So we're going to want to find the new node equivalent of this old neighboring node. Okay, and so the last thing that we're going to want to do here is basically we want to return like the initial, or basically the new graph that we constructed here. And so we can just say, okay, this is our existing head. So we're just going to return basically the old head of our graph. So it's going to be basically the pointer pointing to our new head of this new graph. So let's go ahead and try running that. Oh, the indentation level. I think I just have to add a space here. Key error. So new. So I can't just say new here. Or yes, I can. New, old to new, neighbor. Let's see what's wrong here. Is there the edge case where? Yeah, so one edge case here is we're going to have to say, okay, if there's no head here, we're definitely going to want to return none. That's just one edge case for one of those ones later on, but I guess this is another issue. So new neighbors dot append old to new. So we're iterating through our lookup table here, and we're saying, okay, new neighbor dot append old to new at this neighbor. Can we print this neighbor.val? And so we want to make sure that we're doing this right here. So while we have something on our stack, we want to pop that node, add it to our visited set. Oh, so we want to say, okay, if this neighbor has been visited before, because we're adding to our visited set, then we're checking the node here, but we're really trying to limit the neighbor here, like so. Like so. All right. And success. So sorry about that little mishap here, just this issue where we basically wanted to add this to our visited set. And oh, we don't need that print statement. But yeah, that's pretty much this algorithm. So let's move on to the next one. So here what we want to do is we want to find all the grid locations that can touch both the Atlantic and the Pacific Ocean. And the way this happens, essentially you want to think about this as water just kind of raining down on these grid locations. And so think of these as mountains of different heights. So like this would be 5, and then this would be like 4, and this would be 3. And so essentially water could rain down on 5 and kind of trickle down the map like so, and basically reach the Atlantic Ocean. And also 5 could go downwards to 3, down to 2, and then reach the Pacific Ocean. So we want to say that the grid location 5 could kind of reach both the Pacific and the Atlantic Ocean. However, 3 can't, because it can't basically climb up to 4, or it can't climb up to 5. It can only move to grid locations that are basically shorter than it. All right, so typically what you're going to think of when you're solving any graph algorithm or any algorithm at all is you want to look at this at every possible kind of direction. And so we're going to solve this actually from outwards inwards rather than from like inwards out. And so the way we want to frame this problem is that, okay, what can the Atlantic Ocean reach and what can the Pacific Ocean reach, rather than what cells can reach the Atlantic and reach the Pacific. And so what we're essentially saying here is we're trying to find two sets. One is Pacific can reach, and the other is basically what the Atlantic can reach. And then we're just going to return this set here in the middle that basically the Pacific and the Atlantic can reach these cells here, both of them. All right, and so essentially what we're going to do is we'll design a depth-first search algorithm so that we can basically explore this graph. But we're first going to do it for the Atlantic Ocean and then the Pacific Ocean. And so we're just going to start our depth-first search calls basically from this line here and from this line here, just so we can build that set of what we can reach. And then we do the exact same thing for the Pacific, and then we'll take their subset. Okay, and so if it doesn't make much sense, I really think the code for this problem really helps. So we'll go ahead and implement it. So essentially here, we're going to design a depth-first search function. And so we want to say, okay, we want to make sure that we're within the bounds of this matrix. So let's get the basically the number of rows and columns here. So the length, and I like using the word grid, like so. So now we have our dimensions here. We want to say, okay, is this row within the dimension range that's given to us? And is this column location, same thing here. And so we just want to make sure that, okay, we're not kind of repetitively visiting, or I guess like repeatedly exploring the same location over and over again, which causes a cycle or an infinite loop. And so we just want to make sure that this grid location is not in visited. Okay, and so the other thing that we want to keep track of is a previous pointer. And so what that's going to be is what's the previous location that we were at? Because the last thing that we want is to violate that constraint of, okay, we can only kind of trickle down to values that are less than what we previously explored. And so we just want to make sure that the previous is less than or equal to the current grid location. Okay, and so if we pass all these cases here, naturally we're going to want to explore all 4 possible directions. Okay, and so we're basically going to repeat this 4 times, but we're going to want to look upwards, look downwards, look to the right, and look to the left. And with each iteration, we're basically going to be adding to our visited set this particular grid location. Okay, so that's the depth-first search function here that we're going to be calling, but now we want to actually build out how we're going to be doing this, basically from the Atlantic and then from basically the Pacific later on. Okay, so let's go ahead and define that. So essentially, for the Atlantic, we're going to iterate through for every row in this row range. And also same thing, but for the columns, because we want to do the bottommost row and the rightmost row. And so we just say, okay, let's call depth-first search on every single row on the rightmost column. And so what we can call that is basically columns -1. And then here we want to go through the bottommost row, but for every single column in the bottommost row. So for every column. Great, so that is essentially the Atlantic Ocean, but now we want to basically do the exact same thing, but for the Pacific. So we can do that just like so. Here we are. And so what we're going to have here, and I'll just move me over here, is that, okay, we have this set that is basically marking all of the cells that we're able to reach from the Atlantic and from the Pacific here. And so we're just going to want to copy the Atlantic's visited set before it gets rewritten at this spot here. So we'll just say, okay, Atlantic visited is basically visited.copy. Right, so just before it gets rewritten, let's just copy that because we want to know what the Pacific and the Atlantic can reach. And so we're basically building a result set that we're going to return at the end here, and we want to find, okay, return what the Atlantic and Pacific can reach. And so we're just going to say, okay, from this point on, this is our result set. And so let's iterate through for every single grid location here. So it'll be like so, where we just say, okay, for our in the range and for every column in this range, okay, how do we see if both the Atlantic and Pacific can reach it? So that's going to be here. So if this is in our Atlantic visited, and this grid location is in our visited set, then we know that we want to include this grid location because, well, it can be reached by both the Atlantic and the Pacific here. So let's just do res.append this particular location here. Oh, just have an extra bracket. And I just didn't specify the previous location. Okay, so initially we'll just define the previous location as -1 here, just because we know that at each location inside of the matrix, it's always going to be positive value. So we know that this will be less than the initial value that we explore. Well, let's just see what went wrong here. So we just have too many values. It looks like we have too many. So let's just take a peek here. So we are exploring in all 4 directions here. And we're saying, okay, is this column, are we iterating through? Yep, the bottommost, and then also the bottommost row and the rightmost row. And then we copy it. We also create a new visited set, which we do a similar thing here. So one thing here is we're not actually updating the Pacific to go through the Pacific range, and so we want to use the topmost row now, and then also the leftmost row, not the rightmost row, or the leftmost column, sorry. And success. So sorry about that small error there. So essentially, we're just going to want to iterate through basically the bottom. This will be the right. This is basically the topmost, or no, this is the leftmost column. And then this is the top column, or top row, right? Right column and bottom row. Great, so that's another one down. Let's go ahead and we'll implement the course schedule here. And so for this question, essentially we have a number of courses, and we want to basically enroll in these classes that are given these prerequisites. And so you can visualize this like so. So you have course 0, you have course 1, and course 1 requires you to take course 0. And so we can take these courses by first taking course 1, and then later on taking, or first taking course 0, and then later on taking course 1. Now, the way this could be a problem is, okay, if there's a cyclic dependency, like a cycle in our graph, then we know that we can't enroll in these classes, and that's because, well, because 0 depends on 1, so you have to take 1 before it. Before you take 1, you have to take 0, and so it's just an infinite loop here. And so in that case, you want to say, okay, false, I can't take these courses, or for this example, it's true, I can enroll in these classes. So essentially, all that we're doing is, given this graph, return true if there's no cycle. So it's just a cycle detection algorithm. So there's two ways we could do this. We could use Kahn's algorithm, which is kind of designed for this, where you basically count the number of incoming edges within it, and you're basically just evaluating whichever ones have no more incoming edges, and you're just trying to resolve them. But what we'll do today, because we're doing a depth first search and really trying to nail down on that pattern, we'll just use depth first search, and basically it allows you to say, okay, say we're trying to resolve the dependencies for course 0, and it depends on course 1, and course 1 depends on course 2. Essentially, we're creating a recursive calls to these courses and saying, okay, what we'll maintain is a visited set. And so we're just going to add 0, and then we'll add 1, and then we'll add 2. And then the way we see if there's a cycle is if 2 then says it depends, actually, we see that, okay, what does it depend on? It depends on also 1. And so if we look up in our visited set, oh, okay, but we've already visited 1 before, then immediately we'll want to return false here, because, well, we're essentially saying that, okay, and 2 depends on 1, and well, that is a cycle here, and this will never end. All right, so let's go ahead and implement that. So we'll basically return true if we find no reason to return false. And so we're basically just going to iterate through for every, basically, we'll just call it a course ID in the range of the number of courses that we're given here. And so we're going to call depth first search on every single course ID. And if this returns false here, then we'll want to basically return that immediately, because we found a course that has a infinite loop, essentially. All right, and so, but before we implement this prerequisites representation of our graph isn't very useful, because we don't really have a mapping of, okay, course 0 depends on this list of courses. Instead, it goes like course 0 depends on course 1, course 0 depends on course 2, and it's kind of comma separated, but it would be much better if we could just have a list corresponding to that course. So we'll go ahead and implement that just to simplify things. So basically, we want to generate a graph using a dictionary where the default value is an empty list. And so let's go ahead and build our graph. And so it looks like so. So we're going to iterate through our prerequisites. It's hard to spell. And we'll have to say, okay, this particular course depends on this particular prerequisite here. Okay, and so from here, we're going to want to try to resolve every course's dependencies, like so. And so we want to say, okay, let's create our depth first search function here, and we'll pass in the course ID. And so we're going to want to basically iterate through. So for every prereq in this particular course's prerequisites, we'll be calling depth first search on it. And so we want to say, okay, let's call it DFS on this prerequisite. However, we want to skip it if we already resolved it before. Okay, and so we just want to say, okay, if this prerequisite is basically in resolved, so that's going to be a set here, resolved. It's kind of like a visited set, or it is a visited set. It's just a better name for it because it just means that we already resolved this course's dependency before, and we don't want to do it over and over again, which is not performant. And so basically, if we reach this far, we're basically saying that we resolved this course ID. And so if it's in resolved, we just want to skip it because we already know that we've resolved it before. Okay, and so we can actually name this like resolved if you prefer, because that's what we're doing here. It's at resolve. So let's resolve this course ID, and if we already resolved it, then let's skip it. And so the only other thing is we have to check for that cycle. And so we're basically maintaining what the current path is, and so what courses are in this path. And so we just create a set called path. We're basically just adding and removing from this path as we resolve these course dependencies. Okay, so if we already see that we're trying to resolve this course dependency, if we see it again, then we know, okay, we can never resolve this because there's a cycle here. So if this prerequisite is in our path, or this returns false, then let's return false here, because there's no way we can ever resolve it. So we'll just say, let's return false, or let's return true if we never find a reason to say that there's a cycle. Looks good. And success, so that's another algorithm down. It's basically a cycle detection algorithm, so it's super handy, and you use them a lot on these graph algorithms. All right, so I think this is actually the last one, but we actually have to do this one before it. So there's just two left, and we're actually just going to be pretty much reusing the same code. We're just going to write like 3 lines differently, so it's going to be very similar. And so this is using union find, which essentially whenever you see that you're dealing with connected components, or even like finding cycles within connected components and so forth, you immediately want to think of union find, because it's literally designed to handle these types of problems. And so generally when you solve a union find question, you have to write like a union class or union find class. And so all that we want to do is basically figure out, okay, how many components are connected, and there's 2, because you see there's 2 individual kind of graphs here that are connected. While this one, there's 1 because there's basically just one graph that is connected. They aren't kind of split apart. Okay, and so we'll design union find for that, and I'm already expecting you to kind of know what union find is, but you're going to use it a lot, so it's really important that you kind of memorize this blueprint code here. And so essentially we're going to define our constructor here, and so we'll want to specify the number of nodes that we're dealing with. And so typically you want to say that, okay, what is the parent in this component, but then also what is the rank for this component. And so from here, we basically want to say, okay, this is the rank, and initially it's just going to be 0 for every single node here. And then the parent, well, it's basically for every single node, its parent will be itself. So that means that initially, at first, every node is a root node. Okay, but we basically want to, as we connect them all, they'll share common roots as we move along here. And so the other 2 methods that we want to implement is union, of course. So unioning basically node 1 and node 2 here, like so. And then also we want to implement the find. So let's find the root of a particular node. All right, and so let's implement this one here. So essentially what you want to say is, okay, if the parent of this node is not itself, then we'll want to keep iterating up the chain until we find that parent. And so we just say, okay, then the parent of this node will just be the recursive call to this find method of itself. So self.parent of itself. And that's essentially the find method here. So it's basically using a compression just to shorten that chain. So this runs, I think, in a log n time. And we're saying that, okay, until we see that we found the root, so we know, and this is how the union find algorithm works, that if the parent is itself, then we found the root. So this is basically finding the root. So from here, we just want to say, okay, well, the first thing is we want to find out the roots of these nodes, which is basically just using the function that we just implemented above, like so, self.find node 2. So now that we have the roots, we basically want to compare now. Okay, if they're the same, we don't have to do anything. So if root 1 is root 2, then let's just stop here. Otherwise, essentially the way you figure out which ones you kind of connect together is you just have to say, okay, whichever one has the higher ranking, it's going to be favored as the new kind of root leader. And so we'll just say, okay, if self.rank of root 1 is greater than the rank of root 2, then we'll basically say, okay, then the rank of root 1 is getting incremented by 1 because it's bigger than the rank of root 2. And then also, then the new parent of root 2 will then be root 1 here. Oh, like so. So self.rank of root 1 gets incremented, and then the parent of root 2 is now root 1. And then basically, we're going to do the opposite of this afterwards. I'll just move me over here. So root 2 gets incremented, and then this becomes root 2. Just all template code that's really important for you to memorize and just try to understand here. So from here, what we're going to say is then, okay, well, how do we actually make use of this union find implementation here? Oh, I have some extra spaces. That all looks good. So to do this, we just want to say, okay, let's iterate through for every single edges here. And we're basically going to union these nodes together. So let's union X and Y. And then we want to actually call our constructor here so we can make use of that object. And so essentially from this point on, all that we're going to want to say is, okay, what is the total number of components? And all that is basically, okay, what is the number of roots in our graph? If there's 2 roots, then that means that there's 2 individual graphs. If there's 1 root, there's 1 individual graph, because you're basically constructing trees here. And a tree will only have 1 root. And so if you have 10 trees, you have 10 graphs, so you have 10 components. And so we're basically just going to count the number of roots, and we can just do it like so. So for every single node in our graph, so I believe it's like so. Yeah, so for every node in our graph, we just say, okay, if this node is itself, or if the root or its parent is itself, then we found a root. So if for this node, its parent, so self dot find, if u dot parent is itself, then we just found a root node. I believe this is how it works. Oh, that's the length. So do we have an extra bracket? U dot union X and Y. We have that, I believe. Oh, in edges. Did you forget a comma? Where's that? I for I in range. It's not iterable, so we have a list. I believe that's fine. Oh, the range in the size of n, so it's basically saying for every single node, the value stored in this list will be that node number, which represents itself being the root. Okay, and success. So essentially that's it. So I wasn't 100% sure here, but it makes sense. So if the parent points to basically itself, then that means the parent is itself, and therefore we found a root node, and so we found a new component. And so we just take the length of this array here that we're building. All right, so one more to go. And so actually what we're going to do here is we'll just basically take our union find algorithm that we just implemented, and we'll be using it here for this question. So we're still going to create a object here for our union class, and then we're still going to iterate through for all of our edges, so for x and y and edges, and we're still planning on unioning these edges together. So let's union x and y, and we still want to actually do something similar here. Okay, and so now I'll actually explain to you the question. And so essentially for this problem, what we're doing is we're given a graph, and we just want to see, okay, is this a valid tree? And so what that means is, well, there has to be like one root, and we can't have any cycles. And so naturally a tree can only point to its children. It can't point to maybe another node in its level or above it. And so if so, we found a cycle. And so the union find algorithm is actually great at also detecting cycles, just like Kahn's algorithm and depth first search. And so we can use it here. And so essentially what we want to do is, okay, how do we detect a cycle using union find? Well, we can do it like so. So if self.find, or no, not self.find, u.find of x is equal to u.find.y. And so what this means here is that, okay, if we've already found that we were able to connect these two nodes before, then that means there must be an edge between those nodes that we found prior to it. And therefore, we're introducing another edge that connects these nodes to the same component. And therefore, we found and we're building a cycle. And so it's like saying, okay, if we have Z1 and we have 2 and we have like 3, and we're basically having these edges, but then we introduce this relationship of, okay, 1 goes to 3, that's defined in our edges here, like so. Then we're basically saying, oh, well, that's basically creating a cycle. And we've already found that this is they share already the same root. So that just means that we're basically introducing a cycle within our components here, just like so. All right, and so the only other thing is, once again, for it to be a valid tree, we want to make sure that there's only one root. And because this basically symbolizes what is the number of roots in our connected components, or what is the total number of connected components, we only want one component here. And so we want this to be 1. Oh, what's wrong here? Oh, if this is the case, then we want to return false. Oh, and yes, I just didn't copy that. Oh, let's see what's going wrong here. So in this case, we're saying false, but we should say true. Let's see here. So we're unioning them with each iteration. We're then saying, okay, is the length that? Method is not, oh, like so. Oh, here. So when I accidentally cut out this part here, I said, oh, it's root 1. Because when I copy pasted it was wrong, but we don't want it to be root 2. Sorry about that. Yeah, so that's essentially all 6 algorithms. So sorry about that last little mess up here, but essentially when we were reusing what we designed this class before, we let out on this little last part here, and so I just put 1, but we want to use 2. But yeah, once again, essentially what we want to do is we want to make sure that we're not, don't introduce a cycle here. So this is basically union finds a way of finding a cycle within your graph. And this portion here is just counting, okay, what is the number of roots within our tree here? And if we have more than one root, then naturally this is not a valid tree. All right, so that is LeetCode or LeetCode's Blind75 graph problems here. So I think up next we'll go ahead and we'll solve the dynamic programming one. So that's going to be another long video of 10 problems here, and then I think we'll pretty much finish this series up there. So yeah, so previously I did trees, linked lists, binary search, sliding window, all these other ones, so feel free to check those out. And yeah, subscribe for more. Good luck with the rest of your LeetCode problems. Thanks for watching.